Hello everyone, welcome to the course Manufacturing Processes. I am Kishore Kumar, Assistant Professor in the Department of Mechanical Engineering, MLR Institute of Technology, Hyderabad. So we will start with the overview. So last class we discussed what is the importance of riser, why do we use riser in a gating system. Then we saw how to design the riser. So we saw just the basic principle and we saw two basic principles are there. First one was that the metal solidification time in the riser should be more as compared to the metal solidification time in the casting, so that whatever the shrinkage is there in the mold cavity, riser can easily fill that. And we also saw the second thing, the volume of the riser should be greater than the shrinkage volume which has occurred over there in the casting. So these two principles we saw last class, and also we solved one numerical based on that, so that the concept will be more clear after doing that. Today we are going to see what should be the appropriate shape of a riser, and also we will see what should be the optimum size of a riser. Okay, so we will take two cases, one we will take for the top riser and another one we will take for the side riser, and we will derive the relation and we will see that what should be the optimum size, means what should be the optimum diameter and what should be the, if height is there, so what will be the optimum height of the riser. So first of all we will start with the best shape of the riser. We have already seen that in last class that what should be the basic criteria to design a riser, and we saw that the solidification type of riser, if we are writing this TR, this should be greater than solidification time of the casting. Okay, na? So that is the basic criteria, and we also know the solidification time of in casting we can write T is equal to this constant which is dependent upon the material that we are going to cast upon into volume upon surface area and a square of this one. So from here if we are taking for the riser, so we can write solidification time for the riser, this will be equal to gamma times volume upon surface area and a square of this one. So from here we can see this solidification time is inversely proportional to a square of the surface area of the riser. Okay, so we can say that if the surface area of the riser is minimum, solidification time will be more, that we need for the design of the riser. So what should be the optimum size? If we are taking volume constant, suppose we are taking volume is constant, volume is a constant for the riser, then we know that for a given volume or for a constant volume, the minimum surface area exists for a geometrical figure, and that is actually a sphere. So we can write here for given volume, for given volume, the minimum possible area or geometrical shape can take is a sphere. So from this mathematical analysis we come to the conclusion that the shape of a riser, the shape should be spherical. But the problem with this one is, one, when the shape of the riser will be spherical, we know that when there will be a sand casting, the placing this spherical shape over there, and once after casting taking out this one will be very difficult. That is the reason a spherical shape riser is not used in a riser design. So second best that shape which is generally used or frequently used for a riser design is cylindrical shape. So why cylindrical shape is used? The reason is it's very difficult to place a spherical shape in, especially in sand casting. That is the reason cylindrical riser is generally used in almost all the casting processes. So if you will place this one, so now it may be placed on the top of the casting, it may be placed on the side of the casting. So we come to the conclusion after this mathematical analysis that the riser shape should be a cylindrical shape. Its shape should be cylindrical. Now where it will be placed? It may be placed on the top of the casting, it may be placed on the side of the casting. So depending upon that, we will find out what should be the optimum size of the riser. We have already seen that last class that the minimum size of a riser should be sufficient so that it will be capable of filling the mold cavity, or not mold cavity, in fact it is the shrinkage cavity or the shrinkage volume over there in the casting. That of course should be the minimum criteria, but how much it should be, what should be the optimum size, so that there will be no wastage of the material as well as there will be no underfilling of the shrinkage volume in the casting. So we will see in next slide. So what should be the optimum size for the top riser, that we are going to see what should be the optimum size. So we have already seen that this solidification time for riser. First we will draw this diagram. Suppose this is the casting part and we are telling metal is in this one, and suppose this is the casting and we are placing our riser on the top of, exactly top of this one, okay, and already we have seen that it should be of cylindrical shape. Suppose the height of this one is h and diameter is, suppose this is a small d, okay, this is the riser, this is the top riser we are placing on this one. So we have already seen that this solidification type of riser is inversely proportional to 1 of the square of the surface area of the riser. This is inversely proportional, we have already seen that. So if we will write the surface area of this one, so I am drawing this separately. Suppose this is the riser, okay, so this is the bottom part and this is the top part. This diameter is a small d, we are assuming, and this height is a small h, okay. This part is actually the interface of this casting and this riser, and as metal in this section and this section both are almost at same temperature, so here there will be no heat dissipation from this area, there will be no heat dissipation because temperature will be almost constant. So what are the area of the riser from which heat will be dissipated or cooling will happen? So this is the area, this is the area and this is the area. So what will the area? If we will write the value for the area or the surface area from which heat actually will be dissipated. So area of this one, this cross section is circular actually, so we can write pi upon 4 and a square of the diameter. So pi by 4 d square, and this curved part area will be, so curved part area will be pi and d diameter and this h total height. So this is the area of riser. So this is AR is equal to pi by 4, the area of this top section plus this curved part area. Now we can see this area is a function of two things. It is function of diameter of this cylindrical riser, and also it is the function of height. So what we will have to do, already we have assumed that the volume is constant. So if we write the volume expression, so we can write volume of the riser is equal to, we can write pi upon 4 d square into h. So if we write this v, so this v will be equal to pi upon 4 and this d square into h. So h is equal to 4v upon pi d square. Now as v is constant and this v is constant, so we can see if we replace this h with this h, so we can see this whole expression will be function of diameter only. So we will put this value over there, this h value in this one. So this expression AR will comes out, this AR will be pi upon 4 this d square plus pi d into this value will be 4v upon pi d square. This pi d and pi d will be cancelled out, okay. So finally this will comes out pi upon 4 this d square plus this 4v upon d. So this is the value of the area. We have already seen that this area should be minimum. surface area should be minimum from this expression, so that this solidification time for the riser should be maximum. That is the basic requirement. So for minimum, this one will differentiate this one with the respect of this diameter, because this is the only variable here in this expression, that is diameter d. So if we differentiate this expression with respect to d and equate this to 0, so we will get the value of minimum area. So what we will do, we will take the differential coefficient of this one, this AR, with respect to this diameter small d. So if we will differentiate this one, we will see this will comes out, this value will be, will differentiate, we will see this value will comes out. So this will be twice d, so this will be pi upon 2, and this will be d minus 4 v upon this one will be d square. This value will comes out d square. Okay, so and this should be 0 for minimum value. If we will solve this one for d, we will get the value d optimum. So this optimum will comes out, this value will comes out twice, this value will comes out twice, and v upon pi 1/3. This is the optimum value. If this value will put in the expression for h, we will get the will get the this h optimum, and this will comes out, this value will comes out v upon pi to the 1/3. So from here we can see that this expression, from here we can see that d is equal to, where is the d, this d is equal to, d is equal to twice of h. We can write diameter is equal to twice of h. So these three expressions are very important that we need to remember. So what we got from here, what should be the optimum size of a top riser? So its optimum diameter should be twice of volume upon pi to the whole power 1/3, and its optimum height should be volume upon pi to the 1/3. And from here, if we will see, this diameter should be equal to twice of the height. So this is very important relation, and generally numericals based on these concepts are directly asked based on this one. Okay, so this concept is very important to understand. Next we will see what will be the optimum size for the side riser. So side riser means, suppose this is the part of our casting, so this is the cast area, mold area, and side means, suppose we are placing this riser at the side. Okay, so only this section we can see here, only this part is common, remaining part is not common with this one. So important thing to consider here is, here all the area will be open for heat dissipation, all the section will be open for heat dissipation. Why? Because you can see this is now not actually insulated. Insulated means simply it is not here. Here it was not heat dissipation in the case of top riser, because these two common area were at the same temperature. If temperature is same, so definitely there will be no heat transference. But here we can see all the parts are open for heat transference. So what we will do, this is actually circular cross section, because this is cylindrical shape. So now what will be the area in this case? Surface area. So this will be area of this one and area of this one. So we can write twice pi upon 4 this d square plus area of this curved section. We have already seen this will be pi dh. H is the height of this cylinder and d is the diameter of this one. This is actually d. So now this is twice pi upon 4 d square plus pi ds. This one we can write, this will be 2. So we can write pi upon 2 d square plus pi dh. We have already seen this area in this expression is function of diameter and height. So we can replace this height. We can see from the previous slide that we can replace this height with 4v upon pi d square. So we can write this expression pi upon 2 this d square plus pi d into, we can write 4v upon this pi d h. So pi d square actually. So we can write this pi d square. So this will be cancelled out from here. So we can finally write this one, pi upon 2, this is d square plus 4v upon this 4v upon pi d. This is the area. Now we need the minimum area, that is the basic requirement for the riser design. So what we will do, we will differentiate this expression with respect to diameter. So what will be the value? This is pi upon d square. So simply this will be pi d, because this will be twice d. So this will be cancelled out. So simply this will be pi d minus 4v upon, sorry, this pi was cancelled out from here. This pi was cancelled out. So this was d only. So this will be minus 4v upon d square. Okay. So what we got, and this should be equal to 0. So what will be the minimum value if we will take from this? So this implies d optimum is equal to, we can write this value, d optimum is equal to, I am writing 4v upon this pi to the 1/3. If this value we will put in this expression to get the value h, we will get h optimum. This h optimum will get 4v upon pi to the 1/3. So what we are getting from this one, for side riser, the value of h and the value of d both are equal. So h is equal to d. So this is for side riser. Side riser. So side riser, and we have derived the relation for the top riser. So in the case of top riser, actually diameter was height was twice, diameter was twice of diameter, diameter was twice of height, and here in the case of side riser, this height and diameter both are same. So in the next class we will stop here our lecture, and in the next class we will come up with the third part of this riser design. We will also come up with some numerical based on this concept, so that it will be more clear. Okay, thank you.